statics, electric fields, electric forces. You'll get some diffraction, and then you have the possibility of some of the earlier miscellaneous topics like polarization, thin film interference, and scattering of light. Some of the things that I covered since the last midterm, telescopes and microscopes. But that'll be on a little bit lower emphasis. The main thing that is critical is chapters 21 and 22. This is where more than half, maybe between half and 2/3 of the stuff will come from chapters 21 and 22. We'll have one concept question from today, so that won't require any mathematical calculation, but will involve the concept of Gauss's law or related subjects with the properties of conductors and how that relates to Gauss's law. But it's not a tricky one, so I wouldn't spend a lot of time working on the homework problems or necessarily even reading super carefully through chapter 23 to get ready for the midterm. The main thing would be, can you set up the integrals? Can you do the electric force, electric field calculations for point charges? Could be a kinematics problem, a constant acceleration, and those kinds of things. So if you've been following what we've been doing in class, it shouldn't be a huge leap to be able to do well on this exam. It's not going to be the kind of thing where, oh my gosh, I've never seen this before, what am I going to do type of thing. They should be fairly familiar things, maybe a slight variation, but nothing really new or different that you would consider to be tricky. And what I think is going to be important about today's lecture is that we're going to hopefully further solidify the concept of what an electric field is and how to calculate it. And one of the results that we started with in chapter 22 was the idea that electric field for a point charge was equal to kq over r squared, and some unit vector that points in the r hat direction. So here's our electric field. This is our distance r away. This is our unit vector in the r hat direction. It's the magnitude of E times the direction, where the direction is our spherical coordinates r hat. And so but we started with this rather than deriving it. And so as the first example of how to use Gauss's law, I want to derive this expression. But in order to derive it, I'm going to need to introduce what Gauss's law is. And so we'll, first of all, take a look at the concept of electric flux. Okay, so here we can define electric flux as being the strength of the electric field over the area. Which I can write as E dot A, where E is a vector that points in the direction of the electric field. And for this expression, by the way, we'll assume this is true if and only if E is a constant over the area. If the electric field isn't constant over the area, we can't write this. This is the simplest way to get started with the definition, is to look at this special case situation where we've got a constant electric field over an area. And so the flux then is a measure of electric field intensity. Meaning that if we've got more electric field crossing that area, then we've got more flux. So that means that there's more electric field intensity if there's more electric field over the area. And so what's this like? You know, I know electric field is an abstract concept to begin with, but what is this like? Well, we could if we thought of these as being like rays of light, we could talk about the power as equaling intensity dot area. We think of the intensity as having a directionality that's in the direction of these rays. And so intensity is power per unit area times area. And so this would be the total amount of power crossing that surface. And so that would be a measure of energy intensity. Okay, so we've got a certain amount of energy. That might be in the form of photons, rays of light that are coming in and are hitting the surface. If enough of them hit that surface, it could cause the surface to even melt. Okay? But here, we're talking in terms of, well, there must be a lot of charge to create more electric field intensity. And so somehow then, this electric, what the power is related to is the source. This could be like the sun or something. That's the source. What's the source of the electric flux? Well, the source is what the source of electric field is. The source is charge. Why? Because charge makes electric field lines. Just like the sun here creates photons. Okay, so the sun is the source of this power. The source of this electric field intensity is charge. Okay, so that's the cause and the effect. The charge is the cause, and the electric field intensity is the effect. So we can write this then as the flux is proportional to the charge. Or here, Q is the charge that creates the electric field. And so what's the proportionality constant? Well, it's been experimentally measured to be 1 over epsilon naught, where epsilon naught is a relative of our Coulomb constant, K. This is something you may have already seen in the book, but I haven't written it this way yet in class. 1 over 4 pi epsilon naught. So K is our Coulomb constant, 9 times 10 to the 9 Newton meters squared per Coulomb squared. Epsilon naught is 1 over 4 pi K. So if I plug in what K is there, I get that epsilon naught is 8.85 times 10 to the minus 12. That has units of Coulomb squared per Newton meter squared. And so in the book, sometimes they start out with epsilon naught, but in the problems that we've been doing so far, it's more convenient to just write in terms of K, so I didn't want to confuse the issue. But now, epsilon naught is going to be a more fundamental quantity now that we're into Gauss's law. But we can always switch back and forth between epsilon naught and K. And so this epsilon naught is our constant of proportionality between the charge that creates the electric field and the electric field that's produced by the charge. Okay, and so for the moment, I'm going to leave this out, and I'm just going to talk a little bit about how you calculate flux. But our strategy in these Gauss's law problems is going to be to, what are we trying to do here? Well, our goal is to find, this is usually our goal, is to find the electric field if we know the charge. How do we do that before? In chapter 22 method, we wrote integral of dE equals E. That's the integral of k dq over r squared. And we have many variations on this. But we just integrated a bunch of little dE's to get the total electric field. So here, we're going to get it from the charge distribution in Gauss's law. So that's what we're trying to do with this expression. And so let's just get used to how we calculate flux first. And then I'll apply this to the different examples that we've already looked at in chapter 22. So basically what I'm going to be doing today is showing you how easy some of these problems are. The infinite line of charge, the infinite plane of charge, the point charge. We can get all those electric fields in one step. We don't have to go through that huge, long rigmarole of integrations and figuring out the charge as a function of distance and which components add and cancel. All of that stuff, we can forget about that, and we can solve the problem in one step using Gauss's law. So Gauss's law is considered to be one of what we call Maxwell's equations, which are the fundamental equations that govern the principles of electricity and magnetism. And so for our example then, E dot A, where E is constant over A, flux. Let's say that the electric field were equal to, let's say 100 newtons per coulomb, and the area was 2 square meters. And so that's the area of this thing. Then what we would need to do is take a quick look at how the electric field is oriented with respect to the normal, or the area. Now, area is not considered to be a vector, it's a scalar. So how do we make area into a vector? Well, we define the area to be equal to the magnitude of the area times some unit normal, where that unit normal is a unit vector that's perpendicular to the surface. But with a magnitude of 1. Because it's a unit vector. That's our definition of a unit vector, is a magnitude of 1. So here, I can draw my unit normal, and we notice that in this case, it's in the same direction as the electric field. So what that tells us then is that for this orientation of the area, I have a maximum flux. And so our dot product, E dot A, is just equal to the magnitude of E times the magnitude of A times the cosine of theta. Where theta is the angle between E and A. But since the direction of A is related directly to the direction of the unit normal, it's the angle between E and the unit normal. So once we have the unit normal here, we see that we're getting a maximum amount of flux through this area for this particular configuration. Let's say this was 1 meter on a side, like that. Actually, let's make this 2 meters by 1 meter, so that we have an area of 2 square meters. Then our electric flux would be equal to 100 newtons per coulomb times 2 meters squared times the cosine of 0 degrees. And that would be 200 Newton meter squared per coulomb. And that would be our electric flux. But what if the angle was, say, 30 degrees? So let's turn this thing a little bit. So here's our unit normal, and here's the direction of the electric field, and the angle is 30 degrees. Can you see in this situation, the projection of the area onto this horizontal surface is going to be less area. And so therefore we have less flux. Just like if you have sunlight coming in the wintertime, you don't need sunscreen. There's less power, less energy per unit time hitting your skin, and maybe you should still wear sunscreen, but typically, I don't anyway, not in the wintertime. Because the flux of the radiation, it's not over this area. When the sunlight's coming straight down like this, then the power is concentrated, the energy is concentrated over this smaller area. But here, it's spread out over a larger area. Okay? And so that means that the intensity is less. And so similarly, the electric field intensity is less. If theta is 30 degrees, then this is going to be flux E, be 100 Newton per coulomb times 2 meters squared times the cosine of 30 degrees. So that would be square root of 3 over 2 times 200, 0.866 times 200. And so that would be like 172 or something. And that would be Newton meters squared per coulomb. So we would have a lower flux because we have a less favorable orientation. The unit normal now is pointed this way, so there's less effective area being exposed to the electric field. Then if you went to the most extreme situation where theta is 90, then the plane would be oriented like this, the unit normal would be this way, and none of the electric field lines would cross that area. So the flux would be 0. So the minimum amount of flux happens when the electric field and the unit normal are oriented at a 90-degree angle to each other. And this is normally what we'll see. It's either this or it's that. It's usually not something in between for the kinds of problems that are most easily solved using Gauss's law. So that's the way to work with flux. But how does the flux relate to the electric field and to the charge? Well, this is true if the electric field is constant over the area. But if the electric field varies over the area, we have to integrate. So then we would have flux, and this is our more general expression, is the integral of E dot dA. Where at a particular point, you can have a little tiny bit of area, dA. You have a unit normal pointed away, and then an electric field that would have some orientation with respect to that area. And then you'd have to sum them all up to get the total flux. So in this case then, you'd sum up that little bit of flux. This is like a deflux. It's E dot dA. And the dA always has a unit normal that points straight away. But the electric field for a point charge also points straight away. And so we can say, well, what did we decide before? We said before that what causes this is charge, and that the electric flux is proportional to charge. So we can write this then as Q over epsilon naught, where Q is the charge that's inside of the surface defined by A. And epsilon naught is our Coulomb constant, 8.85 times 10 to the minus 12. Coulomb squared per unit meter. So this is Gauss's law. Sometimes it's written as a double integral over a closed surface. That kind of notation is a little fancier than we need for the kinds of problems we'll be dealing with. But when we put this little circle in there, it means that we're integrating over a closed surface and not just over a flat surface. In the examples I've been looking at so far, we were integrating over a flat surface, not a closed surface. But Gauss's law requires that we surround the charge, because that's the only way we can count all the electric field lines, is if we surround the charge. It's like you've got a fugitive that's trying to escape from justice. What you do is you set up a perimeter, because the fugitive can run in all of those different directions. And so if you don't have a perimeter established, then he may sneak out through one of those places where you have to check. And so you've got to check. Make sure you've counted all those electric field lines by surrounding the charge with a closed surface. So this is our strategy then for applying Gauss's law. This is the source charge. This is the source of the electric field. So if you didn't get that stuff before in chapter 22 about the fact that electric fields are produced by charges, and that that's different from electric force, then you're definitely not going to get this. So that is critically dependent on you understanding what we were talking about before with what an electric field is. And I keep hearing stuff about, okay, well here's our plane of charge, and then here's another charge there, there's a force on it. No, that's not what we're talking about. We're talking about just the effect of the charge producing an electric field at that point. That's the point. I can't say that enough, because that's the thing that tends to mix people up the most from having taught this a few times before. All right, so our strategy then is that we surround the charge with a surface. So this is called a Gaussian surface. We integrate over the surface and set equal to the charge enclosed by the surface divided by epsilon naught. Remember, that's the source charge. This is the total charge inside of the area divided by epsilon naught. So why are we using epsilon naught now and k before? Well, because epsilon naught is a simpler way to write this expression. And this is one of Maxwell's basic equations. And so the Coulomb constant, 1 over 4 pi epsilon, is just kind of a special case that works really well for point charges. That later on we'll see that the speed of light is equal to the square root of 1 over mu naught epsilon naught, where epsilon naught is our electric constant and mu naught is our equivalent magnetic constant. And so there is more of a basic relationship going there between epsilon naught and the basic laws of physics than there is with K. That we should be able to work back and forth anytime that we want. We should be able to just say, okay, well, I know that K is 1 over 4 pi epsilon naught, so epsilon naught is 1 over 4 pi K. So it's not meant to be confusing. You know, defining a couple of different constants like that is not the greatest, but it's the way it's kind of evolved to handle certain types of problems. So let's look then at what this prescription would be for a point charge. Remember, this is our strategy, and this is our goal is to find E. So this is just another way to find the electric field. Or equivalently, if we knew E, we could find the source charge. So we could work either way with that. But typically, this is the way I'd like to introduce it, is that we know what the source charge is and we want to find E. So we go, okay, well, here's our charge. And so all the electric field lines are pointing out from that, that have I chosen the right symmetry for integrating over this surface? This is the integral of E dot dA. Then, over this top surface, can you see that the electric field angle is constantly changing? That's a problem. Also, R1 is not the same as R2, and not in general the same as R3. So if we use a Cartesian integration coordinate system, it's just not natural for the electric field patterns the way that they exist here. And so although this is following the strategy, it's a dumb surface. Okay? We want to be strategic about the kind of surface we use. Now, one thing we could say from this is we could figure out how much flux is there across one face. Because we could say that flux 1 equals flux 2 equals all the way out to flux 6. This is, say, side 1, 2, 3, 4, 5, 6, like that. We've got 6 different faces, and from the symmetry of this problem, if we put the charge right in the center, we have the exact same integral 6 different times. And so if we say that that's equal to the charge enclosed over epsilon naught, that means that flux 1 has to be the charge enclosed divided by 6 epsilon naught, because each one of these are equal. And the sum of those fluxes, from I equals 1 to 6, equals Q enclosed over epsilon naught. So we could say from this that if we know what the charge enclosed is, we could get the flux. But big deal. Why do I really care about that? What I really want is the electric field. The electric field requires this gnarly integration, because the electric field is changing from point to point, and the angle is changing from point to point on the surface. And you've got these corners. What do you do there? It's just a nightmare. But what if we choose a smarter surface? So we'll surround it with a sphere. That's something that's natural to the geometry of the electric field lines and should give us a much easier integration. As a matter of fact, the integration is going to be trivial if we use a spherical surface. So when I say here, be strategic about which surface you choose, what I mean is choose a surface that has the same symmetry as the field lines. And this gives you a trivial integration. This looks like a gnarly problem here, but it's a trivial integration if we do it that way, because then the electric field at all these different points on the surface at a distance r away are going to be the same, because we're the same distance r away in each case. And you go, well, but they're pointed in different directions. So remember, it's the integral of E dot dA. And so each of the little dAs has a unit normal that points in the same direction as the electric field. And so it's really essentially just the same thing as saying EA. Do you see that? Because remember before when we did this for just a surface, it was E times A because E was constant over the surface. Well here, the magnitude of E is constant over this closed surface because it's the same distance r away from the charge. And then when we figure out how the dAs relate to all of that, even though the E here is pointed in the opposite direction from the E up here, the unit normals are pointed in the same direction as E for both of them. And so this is what we end up getting there. It becomes, although it's an integral, if we understand the concept that's going on here, it's a trivial integral. We can say then that E times dA times the cosine of 0 degrees, that's our flux, because every one of the EDAs has a cosine of 0. So this little dA, this little dA, they all have the normals pointed in the same direction as the electric field. Right? So then you can just pull the constant outside of the integral. This is just E times the integral of dA, and that's just E times A. There we go. It's as simple as that. What's A? Well, A is the surface area for a sphere. Now, it's a double integral here, so we could integrate that, you know, r, dr, d theta, all that stuff, but we know what that is, right? It's 4 pi r squared. So that's the area of a surface area of a sphere. Not to be confused with the volume, which is 4/3 pi r cubed. Volume has units of cubic meters. Area has units of square meters. So you can just analyze it from the units if you get them confused. That dV/dr is the same thing as A. The derivative of the volume with respect to the radius is the same thing as the surface area of the sphere. So you should know that. I'm not going to be giving you the surface area of the sphere on an exam. So this is going to be then E times 4 pi r squared. That's our flux. And so that's equal to the charge that we enclose divided by epsilon naught. And so that's it. That's Gauss's law for a sphere. That's all there is to it. As long as we're far enough out so that we're enclosing the charge, and this is a point charge which has a spherical distribution of electric field lines, then we're good to go. So we just solve this for E. That gives us 1/4 pi epsilon naught times q over r squared, which is k q over r squared. Remembering that 1/4 pi epsilon naught was our connecting link between the Coulomb constant and epsilon naught. So we just derived the electric field from for a point charge from Gauss's law. Are there any questions about what we did? This is the simplest example that I know to explain Gauss's law. And what a lot of people will want to do with this is say, well, okay, well that's only going to be true on the surface here of this sphere. But think of this as being like a balloon that you can blow up or deflate. As long as you've got an area that surrounds the charge that has spherical symmetry, it doesn't matter how big the surface is, because it's still just a function of r. Okay? And so if you do it from this point here, then this is some other r, but the unit normals are the same, the electric fields are the same, so the Gauss's law integration does not depend on the size of r. This is E as a function of r. So you can make the Gaussian surface any r you want. And in general, we just choose a representative r, but we could have made the r out here, and the Gauss's law integral would be the same. So in other words, the flux is the same out here as it is in here. But the electric field isn't. Here, the electric field is bigger and the area is smaller. Here, the electric field is smaller, but the area is bigger. But they just compensate for each other so that the flux is the same. Because you have the same number of field lines crossing this surface as you do that surface. And so that's how we get electric field intensity from this, is that the electric field goes down as the area goes up. How much is the area going up? We double the area, then it's 4 times. I mean, if we double the radius, then the area is 4 times bigger because it goes like 4 pi r squared. So that means the electric field has to be 4 times smaller if we double the radius. So that's what gives us our inverse square law. That's the reason why the inverse square law works the way it does. And that's also, in an equivalent gravitational problem, the reason why the force of gravity and the gravitational field from a mass also goes like 1 over r squared. Is that this area of the sphere that has those field lines intersecting it is bigger, but then the field itself is smaller by that same amount, because that's how much the field lines are spreading out. And we're thinking of this as being intensity of electric field lines. Okay, so here the lines are closer together, here they're farther apart. And so that gets back to the idea of how closely spaced are the lines in relationship to how strong is the electric field. Okay, so I'm spending a lot of time on this, but I hope that some of it rings true to you, because what I see so often is just, you think that this one r here is the only r, and that's all that matters in this problem. No, this is like a balloon that you can inflate or deflate so that you can get the electric field changing as a function of r. That's what gives you the electric field as the inverse square law. Any questions about that? Okay, next thing I'd like to do is say, well, what if we have a hollow spherical shell? Nothing on the inside, with a surface charge density of sigma. Sigma is charge divided by unit area. So it's going to be 4 pi times this radius squared. Remember, that's charge per unit area, sigma. So the total charge divided by total area is going to be Q divided by 4 pi r squared. So we have this hollow spherical shell. And let's find the electric field outside of the shell. Where our distance is farther away from the shell than the radius of the shell. Okay, so if we want to do that, we can make the argument that this should have the same flux as the flux of a point charge. Why? Because if we say take the point charge here, we move it out and we spread it out evenly over this area, then if I rotate that, it shouldn't change my electric field pattern. And so just using the fact that this is still a spherical symmetry, what this is telling me is that the electric field line should still be spherically symmetric. Because why would I have more electric field pointing out that way and less pointing out that way if this thing is a perfect sphere? And the charges on the shell, these two are going to have to be equal. And all of these electric fields are going to have to be equal and opposite. If they weren't, if this one were shorter on this side, then if I rotated this thing, then this side would be the longer electric field, and this one would be the shorter electric field. But I haven't changed the symmetry one bit, because this thing has circular symmetry. It's still the same, no matter how I rotate it. So therefore, the electric field lines are still radial, perfectly radial, just like before. And so how does Gauss's law change then? If I want to apply Gauss's law to this, I say the integral of E dot dA equals Q over epsilon naught. So how is that different from the point charge? It's not. It's exactly the same problem. And this is something Isaac Newton was working on with gravity for a while. He basically invented physics. And he started out with the idea of Huygens came to him and asked him if he knew how to figure out the relationship between gravity and distance. And he goes, oh yeah, it's an inverse square law. And goes, it is? How did you know that? Did you have the calculations? They come find his calculations. And so he got going on it to get this going for his friend. And he decided to just kind of invent physics while he was at it. And so he spent something like 18 months on it. And he got the Principia, that has all the laws of physics in it, everything. But he delayed its publication because he was wondering whether you could consider a mass that has spherical distribution as being the same gravity field as if all the mass were at the center. And so what he wondered is, well, we've got some mass elements here that are closer. We've got some mass elements here that are farther away. And it took him a while to figure out that it was equivalent. I think he eventually integrated a bunch of disks and was able to show that it's exactly this mass distribution has the exact same gravitational field here. But it took him 3 years to do it. And he's the guy that invented calculus. It still took him 3 years to figure it out. But when he finally convinced himself that it was the same, then he published his Principia. And the idea is the same here, but we're using the symmetry of the field lines to figure this out, rather than having to integrate an infinite number of disks or rings or whatever it was that he did. Okay, so this is exactly the same problem then. We have a little bit of dA there, the total charge enclosed, as long as it has the spherical symmetry. So we just do E times the integral of dA cosine 0 equals Q over epsilon naught. So this gives us E times 4 pi r squared equals Q over epsilon naught, where E is just equal to 1 over 4 pi epsilon naught r squared times Q. Same thing as before. No difference. So they're exactly equivalent. And this also means that if our sun were to turn into a black hole and just collapse down to 0 size, the orbit of the Earth would be completely unchanged because the force of gravity would not change. It's the same with electrostatic forces too. It's the same kind of reasoning that we use here for R greater than big R. Are there any questions about that concept? Yeah.
Why is cosine 0 degrees again?
Because we're looking at the area, each little d area has a little normal. And if we look at all of them, just like we did before, it's the exact same problem as before. They all point in the same direction as E. So then you can just take the E out as a constant. It's not a constant as a function of R, but a constant R, it's a constant. And so at a constant value of R, we can integrate the area. And we get 4 pi r squared for the area times E. So E then goes down if R goes up by the inverse square law. We can see here because it has to equal a constant value. The flux has not changed. I go out to here, it's still the same flux. It's not 1/4 of the flux out here. It's 1/4 of the electric field. But the flux is the same here as it is there because the charge that created the flux hasn't changed. Any other questions? So this is just one step that the abstraction I found in the past tends to mess people up. Now, what if we're inside of this thing? What if we go inside so that R is less than big R? Then what happens? Well, remember that our rule is that we're counting all the charge that's inside of our surface. So let me see here. I'm going to shade in all of this volume that's inside of my surface. How much charge do I have there? 0 charge. It's all on the surface. And so therefore, we can say that the integral of E dot dA equals 0, because there's no enclosed charge. And so therefore, E is 0, because E is the only thing on the left that can make that happen. So the electric field is 0. And this also works for gravitational fields, too. If you could have a mass, has anybody ever heard of a Dyson sphere? It's, Freeman Dyson came up with this idea. There was actually Star Trek, if any of you were into that did this once, where they had not a charge, but a mass shell. And so the idea then is if you had a dying star, you could put this shell around the star, and you could catch all of the energy and save all of the energy. It would wreak havoc on your astronomical observations, but then you could take all of that energy and take it to your planet, which would be inside of here. The planet's orbit wouldn't be affected by the gravitational field due to the shell, no matter how heavy the shell was. And the same thing is true with a a charge distribution. If there's no charge enclosed, then that means that there's no electric field, assuming that it has spherical symmetry. And so you go, well, okay, but that doesn't exactly make sense to me, because what if you're close to one side of the shell? It would seem like if you're closer to this side, then the effects of this charge would dominate over the effects of that charge that's farther away. So how could the electric field be zero? How could it cancel out? The answer is, for any particular solid angle that you can draw, you're going to have a little bit of charge here, Q1, but over this solid angle here, you're going to enclose some other charge, Q2. If R1 is equal, 2 times R1 equals R2, then essentially the electric field here is going to have 1/4 of the charge, as it does here. Because this has twice the radius of the sphere, and so Q2 is 4 times Q1. If R2 is 2 times R1, because you're twice as far away, and so you're sweeping out a solid angle that is going to encompass 4 times as much charge. But you're 4 times farther away, you're twice as far away, because R2 is equal to 2R1. So if you do this with Coulomb's law, then you've got KQ2 over R2 squared. But that's just K times 4Q1 divided by 2R1 squared. And so that's just KQ1 over R1 squared. So that's the electric field up here. That's KQ1 over R1 squared. The electric field, it should be sitting here. Sorry. This is the source of the charge. So the electric field here is going to be KQ1 over R1 squared, pointed away from charge 1. And for charge 2, it's going to be KQ2 divided by R2 squared. So they cancel. They cancel by symmetry. And so you can do that. I did this for an easy way to calculate it, but it's true no matter what the distances are. If you're inside of there, you are closer to less charge, because you're thinking in terms of how much solid angle it sweeps out. And then if you go to the whole sphere, then you're just adding up a bunch of these things. And so that's the physical interpretation. But you can still just hide behind the mathematics and say, well, the charge enclosed is 0, so therefore the electric field is 0. But using the symmetry of this, we can show that that has to be true. And if Newton had realized that, I don't think it would have taken him 3 years to work the problem out. But he didn't think in terms of that kind of symmetry. Are there any questions about that? Okay, now what if we had a charge conducting sphere? So far we've dealt with a spherical shell, inside and outside. And so let's plot this out. This is for the shell. Value here is R. This is E. And this is our radius R away. Okay, so if we want to plot this up, then we can make it 0 to here. But then once we get to the radius R, then at this point it's going to be KQ over R squared. Because now we're at the surface. And then from there on, it's going to drop as 1 over R squared. for r greater than big R. So this is E equals 0 for r less than big R. And this is E equals kq over r squared for r bigger than big R. And the same thing would be true in this direction too. So I could draw the same thing out this way and out that way. And you could have it out here to here and then out this way. So you'd actually have something that looks like this. But I'm just looking at a cross section over here. For a point charge, the electric field just looks like here. It essentially is infinity because we've got 1 over r squared. So it goes up to infinity like that, E. And here, E is equal to k q over r squared. So it looks like 1 over r squared. But if we continue this plot, it actually goes to infinity. Because when you divide by 0, you get infinity. And then when you go to infinity this way, you get 0. So that's what the plot of E versus R looks like for a point charge. This is a shell. This is a point charge. Next, let's look at a conducting shell. And for this problem, I'm going to make it negative. I've been making everything positive up to this point, but it's a little easier to visualize what's happening if I make it negative. So this is a conducting spherical shell. So that means that inside we have a conductor. This has some radius r. And so what will happen then is that you'll have, just a conductor, you have electrons that are free to move. Let's say we have a net charge. We've added a bunch of electrons to it. Maybe we had a Van de Graaff generator nearby or something. We're able to add electrons to it by whatever means. So what the electrons are going to do is they're going to repel each other until all the charges are as far apart from each other as possible. And because it's a conductor, there's not much resistance to the motion of the electrons, so the electrons just move. For an insulator, the charges would be locked into place. So we'll look at that in a little while. But for the moment, let's say that the charges are free to move. So the net tendency then is to make the electric field 0 inside of the conductor. So the process then, if the electrons will moving, is that the electrons keep moving until there's no electric field inside. So the electric field is 0 inside of the conductor. Why? Because if there were an electric field in there, that would move charge. And so as long as there's an electric field in there, charges will move. And so it's just like in this room. We could have some wind or something that if you close the door and you turn off the air conditioning, eventually all of these motions are going to cancel each other out. If there were a force on a mass creating a wind, then that would indicate things aren't in equilibrium yet. So when we go to equilibrium, we don't want any net forces on any of the charges in here. Otherwise, those charges are going to move until there isn't a force on them. So the effect of this is that all of the charges migrate to the surface. And so they keep repelling each other until the electron winds have all died down. And at that point, they're as far apart from each other as they can be. And by doing that, we've ensured that the electric field is zero inside of the conductor. Why? Because we just showed that over here. If you have no net charge inside of a spherical shell, then there's no electric field. And so this is the same problem now as an electric field acting until the charges all reside on the surface. And so therefore, the electric field must be zero inside of the conductor. And so understanding this then is contingent on you understanding what we did here with all of those arguments that we made for why the electric field is zero if we just have a uniform sphere of charge.
There you say all the excess charge migrate to the surface. Is that in the context of the spherical shell, or all the charges already on the surface?
Well, yeah, but the amount of time that it takes for them to migrate is microseconds. So equilibrium is reached almost instantaneously. And then it's still, it's the exact same problem. So, but while it's going to equilibrium, that's not the case. But it's going to go to equilibrium very fast. And at that point, the charge density is going to be the same over the surface. So that means that the charge is distributed evenly. And that's important. And that means that our charge density, which is charge divided by 4 pi r squared, is a constant. So our charge density on the surface of a conducting sphere that has a net excess charge is constant. Question?
So is that a shell or is it a conducting sphere?
It's the same thing. It's a conducting sphere, but what I'm saying is that the math is identical to a conducting shell. And so it's the same problem. And you could also do it with positives, but then the reason I didn't do it with positives is then what would happen is that the negatives would have to all migrate to the center, and I think that's a little harder to visualize. And so I did it with negative charges. But with positive charges, the same effect would occur, and you would get the same plot. The same integrals all the way through, inside and outside. You have the identical problem, so I don't have to redo all of that. It's already been done for us. It's the exact same problem. But what if the surface doesn't have constant curvature? What if we've got some weirdly shaped surface like this? Well, if the curvature is not uniform, E will still be equal to 0 inside of the conductor. But the surface charge density will change. So in other words, where there's less curvature, there's less charge density. The electrons are farther apart. But when there's more curvature, there's more charge density. Because these things can't cancel themselves out inside of here. They kind of push up against each other, and they conspire in such a way that where we have greater curvature, we have greater distribution of charge. And so actually trying to calculate the electric field around this thing is going to be kind of a nasty problem. Because now we don't have a well-defined symmetry for the electric field lines. The electric field lines are going to tend to converge more here. And then here, they're going to be more spread out. So you have lower electric field outside here and higher electric field there. Then in this area, there's less curvature here even. So these will be a little more spread out. Then a little more curvature there, a little more charge. Then more spread out through here, because there's not much curvature. But where there's more curvature, there's more charge. And it spreads out a little bit. So it's only when the curvature is constant that you get a constant charge density. But when the curvature varies from point to point on the surface, we can always say that the electric field has to be zero inside of the conductor, because if it weren't, then there would be forces that would keep acting until it is, until the electron winds die down. But that forces the charges to migrate into regions of greater curvature and higher concentrations. Okay, so that's a conceptual look at that it's not something that we would do the math for, just because the problem is too complex for us to want to try to deal with that right now. But are there any questions about that concept or about any of these other results? All right, well next, what I want to do is just change one word for case 4. I'm going to make this insulating, but it changes the entire problem. Okay, so here is the electric field distribution then. This is the way we plot it as 1 over r squared for either a spherical shell of charge or for a conducting sphere of charge. But when we go to the insulating sphere, it's a different kind of problem. Because now in an insulating sphere, the charges can't migrate to the surface, and we will have an electric field inside. So we've done this one. But what about this one? Okay, so now we've got charge uniformly distributed through the interior. Call that case 4. That's our last one. So this is the insulating charge sphere. And we want the E for this. That's our case 4. Electric field now for an insulating charge sphere. And by the way, this has an analogy to gravitational problems too. Because you can talk about uniform mass distribution within the interior of a planet. And you can figure out what the gravity field is as you bore down toward the center of that planet. In much the same way as you can find out what the electric field here is as a function of r away from the center of the uniform distribution of charge. Now, when I say insulating, what I mean there is that the electric field can't be zero because it's the charges aren't free to move. They might want to move, but they can't move because they're held in place by a stronger electrostatic attraction of the atoms in an insulator, like a plastic. You're not going to get current flow normally through a plastic, like a PVC pipe or something like that. I mean, you can get charge to flow through something like that, but you need a tremendous amount of voltage to get that to happen, and we're assuming that doesn't happen here. Okay, so what we could say then is that the charge density, which we'll define as charge per unit volume, must be equal to a constant if we have a charge distribution that's uniform through the interior of the solid sphere. Now there are problems, and Mr. Clark is famous for doing these, where you have the density as a function of R. But I'm going to keep it constant for these problems. A little later on, I'll do something with an R dependence, but I want you to try to get the concept going first before I make it more complicated. So charge per unit volume then for this problem would be the total charge enclosed we can make a positive or negative here. But the charge density then would be that divided by 4/3 pi r cubed, where r is the radius of that sphere. Here, that's r. But it's going to be constant because in any smaller volume, if we had half the volume, we're going to have half the charge, because we said the charge distribution is uniform. So that means the charges are evenly spaced throughout this thing. And so that means that it's also equal to little q divided by 4/3 pi little r cubed, where little q is the charge enclosed by a smaller sphere. R is less than big R. And so this is the charge that's enclosed in this smaller sphere here. And that charge divided by this volume is equal to the total charge divided by the total volume. So if we set those equal, this allows us to write the charge enclosed by our Gaussian surface is equal to little r cubed over big R cubed times big Q. I'm just taking this expression, which is one that we get from the fact that the charge density is the same regardless of whether we take a small amount of charge or a big amount of charge, because that divided by the volume is always the same number, which is our volume charge density. This would have units of coulombs per meter cubed. So that's always going to be the same. So this is our function then that allows us to write Gauss's law. The integral of E dot dA equals Q enclosed over epsilon naught. So now we know what Q enclosed is because we constructed a Gaussian surface that's only enclosing the amount of charge that's inside of our radius. But what about the charge that's outside? Does that affect the electric field inside?
No.
We already showed that that doesn't. And you can make that argument. We didn't do it for a spherical shell. We did it for, we didn't do it for a thick sphere with a hole in the middle. But you could always add up a bunch of these little rings. And each one of them would have an electric field that would cancel. So therefore the whole thing is going to cancel out outside of R. So that none of these charges are going to affect what's happening inside. So that's just the same argument that we used before. We had a spherical shell. Remember, you could be closer to one side, but that solid angle being the same as the solid angle out here meant there's more charge at a greater distance over here, less charge but a smaller distance out there. Same deal here. So we're just repeating the same thing again. So each one of these arguments then kind of, you need to get it to get the next step. So here then we can say, well, this is just e times the integral of dA cosine 0, right? Because we still are just summing up the charges that are inside of here. So there's a unit normal. Here's our electric field at each of the little dAs. Okay, so here's our little unit normal here, pointing in the same direction. Same thing as before. We're just doing the same thing over and over and over again.